So let's talk about intractability. Um, we talked a little bit about P versus NP, right? And then we started talking about NP completeness, right? We have this idea that a problem reduces to another problem if the Cook reduction means if we can transform it and solve it with a polynomial number of calls to problem y. So if y is solvable in polynomial time and our size of y given an x doesn't grow too much, then x would be able to be solved in polynomial time, right? Karp transformation requires only one call to y. And we don't really know if they're the same or not. As usual, we don't know tons of stuff. Now, the really important thing is NP complete, which is a problem in NP with the property that every other problem in NP can be reduced to this problem. So once you have this, right, that problem y in NP complete will be solvable in polynomial time only if every NP problem can be solvable in polynomial time. So basically, if P equals NP. We don't know, we believe that's not true, but we don't really know. We talked about circuit satisfiability. Given a combinatorial circuit, is there a way to set the circuit input so that the output is 1? And Cook and Levin in 71 and 73 proved that this is NP complete, right? The way that they did it is basically, if you define your problem over strings, right, then any algorithm that takes a fixed number of bits n as input and produces yes or no can have a circuit, right? And we know that circuit satisfiability is in NP. We have shown that. So if the algorithm takes polynomial time, the circuit's of polynomial size, and so any problem in NP has a polynomial time certifier. That's the definition of NP, right? And it takes the string that describes the problem and the witness, and the size of the witness has to be a polynomial function of the size of the string. And so we could also think of it as a algorithm that takes one string of size of S plus size of P. So given that, we could, whatever it is, convert it into a circuit of that size, right? And so the circuit K is satisfiable if and only if the certifier would say yes. So we can transform any problem in NP into a problem, into a circuit satisfiability problem. And so circuit satisfiability is in NP complete. It is in NP, and any NP problem can be transformed into that. And this was kind of the example um, for transforming this graph and the independent set problem into a circuit satisfiability problem, right? Where on the right we have set of size greater than or equal to 2, because if you have a set of size 2, then you have a set of size 3, right? And so these are the edges. UV, we have an edge, so we have a 1. We have a 0, we have a 1. And this would be the things that the circuit satisfiability oracle would have to satisfy. That tells me which of the two are in there. And by this cool cheating thing, we have shown one NP-complete problem. Once you do that, right, then you can just transform other ones onto that one, and that shows, or sorry, transform that one into other problems, and that shows that other problems are also NP-complete. Does that make sense? If you know that Y is NP-complete, if you know that X is NP-complete, to prove that Y is NP-complete, you just show that Y is in NP, choose a problem X in NP-complete, and prove that X reduces to Y. So that would show you that Y is NP-complete. So every other problem in NP could be transformed to X, and since X reduces to Y, it could also be reduced to Y. Does this make sense? So how could we show that 3-sat is in NP-complete? We know that 3-sat is in NP, because we saw that before, right? The other way of looking at it is also given C is the assignment that would satisfy, right? And you can show that it's solvable in polynomial time, or just testable in polynomial time. And so we need to show that circuit satisfiability reduces to 3-sat. So given a combinatorial circuit K, we need to construct an instance phi of 3-sat that is satisfiable if and only if the inputs of K, or the original problem is satisfiable, right? The inputs of K can give a 1. So what are we going to do? Imagine that K is a circuit, right? We are going to, first of all, create a variable for each circuit element. So that's not just the leads, which are the input variables, but everything in the middle. In this one, we would have 6. And then we can compute, we can create a satisfiability formula that corresponds to this, right? So for this x1, we are doing an OR with these two guys, right? Let's see, what are they doing? X2 is not X3, so we would have two clauses, either X2 or X3, and not X2 or not X3. So that's the conversion for a not. When we have X1 is X5 or X4, we are going to have to add 3 clauses all right. Okay. So this is an AND. So we have not x0 or x1, not x0 or x2, and then x0 or not x1 or not x2. So this become equivalent to the other ones. If you have particular things, then you just add the closest they should be, and then we need to add extra variables to make them 3 sat instead of just sat. And once you do that, you get to a 3 sat problem that corresponds to that circuit, which means that circuit satisfiability is reducible to 3 sat, which means that 3 sat is NP complete. We had also shown that a bunch of other stuff was reducible, right? So by just getting 3 sat, we get all of those guys, right? We get everybody that can go from one to the other because they're all NP complete. In a way, they're all the same really hard problem. They're all almost variations of the same problem, which is incredibly cool, right? We can show that all of those things that look completely different are actually the same-ish. So in terms of genres or paradigms or kinds, right? We saw packing and covering, set cover, vertex cover, independent set, constraint satisfaction, circuit satisfiability, SAT, 3 SAT, sequencing, Hamiltonian cycle and TSP, partitioning, 3D matching, 3-color, and numerical problems like subset sum, partition. Now, in practice, most of the problems that we have studied for a while, that we give them a name and stuff, right? We know they're either in P or in NP complete, if they are in NP. There is a few that we don't know, like factor and graph isomorphism and Nash equilibrium. Now, unless P equals to NP, there are problems in NP that are neither in P nor in NP complete. So probably those guys are, or some of those guys are, but we don't know. We haven't proved it. If you prove it, you become an instant millionaire plus uber famous and rich. Other books, right? There is over 300 well-known NP complete problems, right? A bunch of other things. Mesh partitioning, phylogeny reconstruction. I have no clue what heat exchanger network synthesis is. Protein folding in chemistry, and that's super useful for biology, right? For bioinformatics and that kind of stuff. Equilibrium of traffic flow, and those are probably just flow things, but with cars. Arbitrage in economics, VLSI layout for electrical engineering, and this again is just a graph kind of problem, right? Optimal placement of contaminant sensors, again, a graph. But financial engineering, calculate the minimal risk portfolio of a given return, given the returns and the risks. Nash equilibrium in game theory, some weird integrals in math. Turbulence in medicine, right? Reconstructing 3D shape from 2D things. For operations research, TSP is one of those, but we have a bunch of other ones, and a bunch of the games, right, are so much fun because we are really just searching in graphs, right? I mean, Sudoku and those things. Not all of them, right? Like Rubik's Cube is actually solvable, the normal one. It's fairly easy to solve once you know what you're doing. It's a pain to know what you're doing, but there are versions and variations that will have that kind of stuff. In a way, right, this definition of NP-complete is the prime intellectual report of computer science to other disciplines. Gets more citations per year. It's kind of the most important thing that we have from computer science theory. It's like, these problems, no, don't even think about it. You can't solve them optimally. Is P equal to NP? We believe no. We don't know. But we still believe no. And yeah, we don't know. There are jokes. It's also good for geeky jokes. Now, NP, the definition of NP is asymmetric. We only need certificates for yes instances. We don't say anything about no instances, right? You can't misclassify them. You can't misclassify a no as a yes, but you could have an infinite loop in checking for no. That is allowed. Does that make sense? So, for example, for satisfiability, you have unsatisfiability, right? Satisfiability is prove that a formula is satisfiable by giving an assignment. How can you prove that a formula is not satisfiable without going through all of those things? Or do you have to go through all of those things, right? Again, right, Hamiltonian cycle, your witness could be the cycle. What could be a witness for there is no cycle? Unsat and no-harm cycle are not known to be in NP, right? So we call those guys co-NP. They are the complement of decision problems in NP. Co is for complement, right? Notice that we are defining a problem, right, with a very specific thing. A problem is a set of strings for which your algorithm would return yes. It's a decision problem. A problem is a set of strings, just that the set's infinite, so you specify it with an algorithm, right? And so co-NP is the complement of that set. So it's the set of all strings where the other algorithm would return no, right? Or the other algorithm wouldn't return yes. Is NP equal to co-NP? We don't know. We believe no because if they were equal, then P would be equal to NP. Or actually, if they are not equal, then P is not equal to NP. If P is equal to NP, then that would mean that NP is closed under complementation because P is. And so NP would be equal to co-NP. We don't believe it's true. So if we were able to show that they're not equal, then that would also show you that P is not equal to NP. A good characterization of problems characterizing NP intersection co-NP is we have a succinct certificate for yes instance that gives us NP, but we also have a succinct disqualifier for a no instance. We also have a way to tell you no, right? So for example, for a problem given a bipartite graph, is there a perfect match? We can show that there is by giving you a perfect matching. We can also show you no by giving you a set such that the set of neighbors is less, the size of the set of neighbors is less than the size of that set. And that will mean that there is no perfect matching. So in this case, we have a problem that's both in NP and in co-NP. Some of them may only be in one or the other. P is also a subset, maybe not proper, of NP intersection co-NP. And again, are they the same? We don't know. Maybe P is the one where we have NP intersection co-NP, but maybe not. We don't know. For other examples, linear programming, which is in both, right? Given a set of variables to maximize. What was linear programming? Did you ever see that stuff? No? Okay. It's a famous algorithm. It's a famous for optimization problems, for operations research kind of stuff. And that's one for which there is a good algorithm, so we can do it. Integer programming, no, but linear programming, yes. Primality testing is in there, and it requires a trick, right? It's both in NP and co-NP. If a number is not prime, right, what can be a succinct witness? Of a problem not being prime.
You can provide a number that factors into.
Give you a factor, right? Or give you the prime factorization, right? And that will show that it is composite. But there is this thing that says an odd integer s is prime if there is an integer between 1 and s with those characteristics. And so by giving you those guys, I can prove that that guy is prime. So by giving you a prime-ish factorization of n minus 1 or something like that, t to the s minus 1. Factoring a number is in both NP and co-NP. We don't believe that it is in P, but if it was, what would that mean? All our certificates and keywords and stuff die. Actually, a ton of them. We use asymmetric key encryption, right? We have a public and a private key, like SSH and SSL, right? All of those guys. They are based on combinatorial problems that are NP complete, where if I have one piece of the answer, I can get the other one easily, but if I don't have it, then it's really hard. So one of the original ones was using prime factorization. So I have this humongous number that is actually the product of two humongous prime numbers. And so if I have one and you have the other, we can get the total and do modular arithmetic on our information on it and so encrypt it. But if you don't have, or if you have the total and one of them, right, But if you don't, if you just have the big number, you're doomed. It's going to take you forever to factorize it. And that was the idea. I don't know which algorithms are current. That changes relatively often. It's way more often than algorithms boost. Are we still using RSA? I don't think we do anymore, right? We use Blowfish because RSA is now weak. We don't call it Blowfish, we call it something else, right? Is anybody here doing security or? But if we were able to factor prime numbers, we would break a bunch of encryption things. If we were able to solve a bunch of those P versus NP problems, we would break a bunch of other encryption things. So, we have quantum computers, and this idea of quantum computers. We could, given a quantum computer, factor an n-bit integer in order of n cubed steps. And so BQP is the bounded error quantum polynomial time. Quantum computing implies probabilities. You probably get the answer because that's how quantum mechanics work, right? So we have been able to factor that 21 is 3 times 7. Isn't that cool? We don't know that we have produced quantum computers. If we have, they are in the NSA basement and nobody has seen them. Actually, Google supposedly bought one, so maybe there's one in Google's basement and one in the NSA's basement. This is more historical, right? What's the name, right? Versus, so they were talking about NP hard, which is the one, and they talked about other kinds of names that could use. And they have used those kinds of things for there is other terminology proposals, call it PET, so that now would be probably exponential time. And if P is not equal to NP, would be changed to provably. And then if it's equal, we'll change it to previously exponential time. That was a cute proposal. GNP greater than NP, and so costs more than the GNP of a country to solve. So they have a bunch of those things. However, the non-cute proposal, NP complete, is a problem that is in NP, and every problem in NP is reducible to it in polynomial time. NP hard is almost the same, but we don't require the problem to be in NP. So it includes NP complete and harder. Does that make sense? Some sense. We have tons of time now. And I loved this. This is kind of the super important corollary of NP complete. What do I do if I have an NP complete or an NP hard problem? Well, I almost know that there is no polynomial time algorithm that would solve arbitrary instances of the problem, right? Optimally. So I need to give up on at least one of the three. Either I don't solve arbitrary instances, or I don't solve optimally, or I don't do it in polynomial time. So if I give up on solving arbitrary instances, I come up with algorithms for special cases. And hey, it worked for this special case, and that's what I really wanted. I don't need to do the general case. Maybe, right? If I don't need optimality, and that's right, there is tons of approximation algorithms and heuristics for hopefully getting close. Actually, there's a bunch of algorithms that are provably close, which is really cool. Bunch of approximation algorithms. But if not, you can just like, well, cannot explore every possibility, but I'll explore a bunch of them. Hopefully I found a good one. There is tons of that, search algorithms and things like that. Or I can just say, well, I'll just design an algorithm that may take exponential time if I'm unlucky. And then either solve problems of small sizes or give up on them eventually, right? Put it on AWS, wait 5 hours. If it didn't work, give up. Throw more hardware at it, but at some point in time, just say, right, get a cluster of 100 machines, working on it for 5 hours. If it doesn't work, I give up. This one is not solvable, right? The problem with exponential is that eventually you run out of hardware. For example, the independent set problem, finding a set of nodes, right, that would not be joined, right? Find a maximal set of nodes that are not joined by an edge, right? There is no edge between those. In a given graph, right, we saw that it's NP complete. Now, on a tree, it's not. On a tree, you have at least one node that is a leaf. You have at least one node that is not attached, right? So if that node, right, if you have a leaf, then one of the maximum cardinality independent sets contains that that node. And so given if not, right, find the maximum cardinality independent set. If it contains S, then that's what we wanted to prove. If it's not, right, then there is an edge, UV, right, where V is the edge that I wanted. And then if U is not in S and V is not in S, then adding V to the independent set would increase the size. So S was not maximum, was not optimal. Now, if U is in S and V is not in S, then taking out U and adding V would also give me an independent set, because the only edge is UV, right? The only edge for V is UV. So I can find a maximum cardinality independent set in a forest, which is a bunch of trees that may not be joined at the root, with this greedy algorithm. While there is edges, find a leaf, add it to your independent set, and delete the vertex that you added and every vertex that's connected to it. And then keep going until you're done. Actually, you remove, U and V and all the edges incident on U. Right? Because And this is orderish of n. Maybe n log n if you consider sorting. So does this work if it's not a tree? No, it doesn't. But it does help me solve a special case. If my problem actually involved trees, life is good. There is a similar thing for weighted independent set. Given a tree and node weights, find an independent set that maximizes the weight. I could create a dynamic programming solution which would define opt-in of u as the maximum weight of the maximum weight independent set of the subtree rooted at u and containing it, and opt out of u the subset tree rooted at u but not containing u, and so OPT would be the max. And these are the definitions for OPT in and out. If it is a tree, right, then we can do it by considering the leaves. And going around that. In a way, this allows me to say, oh, these subtrees are only connected through this guy. So I can do special things with this guy, either take him out or something like that, and that reduces my problems, makes them tractable. There is similar things for planar graphs. I'm going to skip. Come talk about the other really cool thing, which is approximation algorithms. A row approximation algorithm is guaranteed to run in polynomial time, guaranteed to solve arbitrary instances of the problem, and guaranteeing to find a solution within a ratio row of the true optimum. So we are not going to find the right one, but we are going to get close. For some problems, that is really cool, right? And that can get me. So, for example, for vertex cover, right? Greedy algorithms are guaranteed that to be within 2. So I may not be perfect, but I'm at most halfway off, which is cool, right? For some of the problems, we have cool approximation algorithms. The knapsack problem is one of the well-known optimization ones. You have n objects and a knapsack. Item I has value vi and weight wi, and your knapsack has a weight limit of w. So the idea is fix the knapsack so as to maximize the total value. What are you doing? How would you brute force this one?
Every possible combination of items?
Yes. How many possible combinations of items do we have?
In factorial?
It's subsets, right? So subsets is what? The set of subsets of a set of n things has 2 to the n, right? Basically, each one of them you could either include, each item you could include or not. So you end up with a binary number of n digits, right? Does that idea make sense? So it's 2 to the n. And the integer knapsack problem is NP complete. I think we proved it somewhere, right? the knapsack problem, this is the proof. Knapsack problem is NP complete. And we're going to prove that by showing that the subset sum reduces to the knapsack, right? It is in NP because we could brute force it in exponential time, right? Which is equivalent to saying that if you give me the that would be a good certifier. But yeah, if we could brute force it in exponential time, that's NP complete. So we're going to prove that the subset sum reduces to the knapsack. Given a set x and values ui greater than or equal to 0, an integer u. So what we're going to do is we're going to create a knapsack problem where for each one of the elements in my set, I'm going to have v and w be the same. And my goal is the target of the subset sum problem. And so then after that, I just check whether the max is equal or not. I can do stuff with dynamic programming. Opt IW is the maximum value of the subset of items 1 up to I with weight limit W. Case 1, right? I do not select it, so it's the same thing, but now I have I minus 1. If I select it, I change my W, so my dynamic programming would be like this, right? It's either 0, if I 0, or opt of I minus 1 and W if Wi is greater than W, or the maximum of that one, or including that guy, so Vi plus opt I minus 1 and W minus Wi. We saw this for dynamic programming, right? Is this polynomial? The answer is ish. It's polynomial of what? It's NW, right? So it's not polynomial on the input size, because I don't know how big is W. It is polynomial on the input size, however, if my weights are small integers, right? So I can cheat. This is the equivalent definition of the dynamic programming. What I can do is, let's see. An equivalent thing, right, is this one, opt_IV, which is minimum weight of knapsack, for which we can obtain a solution of value greater than or equal to B using a subset of items I. We would have a similar dynamic programming solution. Here's a really cool thing. What's my problem? When W is big, right, I'm doomed. Well, let me just divide my W's, right, so that they are small. So round them off, right? Say, okay, let's see, this is, okay, so this is 27 million, right? So I will divide by 1 million. and choose the ceiling. So this is 28, this is 22, this is 18, this is 6, and this is 1. Right? And I want to choose the ceiling to give some value. And then solve that one. And that one is simple. I can just use dynamic programming in there, right? I could, basically, if I define Vmax as the largest value and epsilon is my precision parameter, I define delta as my scaling factor, which is epsilon, my precision parameter, times Vmax divided by n. The optimal solutions in this new space are equivalent, but, right? It's close, but not the same. I'm going to have ties that don't, right? That I wouldn't have on the other side. We have a really cool thing, which is I am within a factor of 1 plus epsilon of the optimal. So I can take something that wasn't polynomial and make it polynomial as long as I don't have to be optimal. I can produce arbitrarily high quality solution, trading accuracy for time, which is really cool. Some other things give me either words bounds or things like that. For max 3 sat, for something like 3 sat, I just have yes or no. So there is no. But this is a variation on it. And I have a 7/8 approximation algorithm, but it's been proved that unless p equals to np, there is no p approximation or row approximation, sorry, for row greater than 7/8. So I know that I'm doomed-ish. The other thing is have exponential algorithms, right? But don't worry about worst case behavior. So basically say I'm gonna run it for a week, and if it didn't work, it didn't work. But chances are that it's gonna work, right? So we can brute force, right, for tree satisfiability. We can try brute forcing and using stuff like this 1.3334 to the n. We can use other kinds of things. This is again for satisfiability. We have efficient SAT solvers and things like that that sort of kind of work. And you just say, okay, that's it. And so this approximation algorithms, right? There are approximation algorithms, and there is also so this is an approximation algorithm for TSP. There is a polytime algorithm to find a tour whose length is at most 1 plus epsilon times that of the original tour. And then we have stuff like branch and bound and a bunch of other heuristics for solving these kinds of problems, which makes our life cool. You're not completely doomed. You're doomed, just not completely doomed. Any questions? Any answers? No? Good. Then I'll give you back 10 minutes of your life.